A delta table can be millions of small files sitting in cloud storage. Run a real query across them, and it takes seconds. Even the best-tuned engines could not reliably beat 1 second. But live apps need an answer in under 100 milliseconds, 10 times faster than the lake could go. So teams stood up a second, faster database beside the lake and copied the data in. That means more machines, staler data, and access rules maintained twice. The real-time Lakehouse removes that copy. The engine behind it is called Reyden. The old stack ran on Spark, on the Java virtual machine. That machine pauses to collect its own garbage, and a 200 millisecond freeze wrecks a 50 millisecond budget. Then came Photon, the math rewritten in C++ using the chip's vector instructions. But it still sat on that same Java plumbing. Reyden keeps the fast Photon core and rewrites everything around it in Rust, the reads and writes, the planner, and the scheduler. Rust frees memory the instant it is done, with no garbage collector, so the pauses that spike latency never happen. Fast reads are wasted if the data is stale, so writes and reads are pulled apart. Live writes land in a Postgres engine. Reyden only reads. Both point at the very same storage. A part called Moonlink watches every change in Postgres and reshapes each new row into columnar form in memory right away. When you query, Reyden reads the files on disk and that memory buffer together as one table. A new write shows up within a fraction of a second before it is ever saved to a file. The honest caveat: there are now two consistency worlds with a small gap between them. A row is committed in Postgres a beat before the reader can see it. Across those millions of files, the log stores the smallest and largest value in each one. The planner skips the files it can prove you do not need before reading a single byte. A background service keeps merging small files to stay lean, and most hot data is served straight from memory, so storage is barely touched. How fast is it really? Treat the vendor numbers as claims and look at the independent tests. One benchmark saw the same lookups fall from about 550 milliseconds to 86. But two limits showed up. 4 times the compute barely helped, because the bottleneck is now the network and storage, not the processor. And some complex joins ran slower than the older engine. One rival reran the test on a single untuned node. It held hundreds of queries a second, and under overload it did not crash, it politely refused new work. Another rival matched the published 100 gigabyte result once its warehouse was configured properly, and pointed to an artificial timeout behind the terabyte comparison. In short, a real gain, framed by favorable benchmarks. So the idea underneath is simple. Keep one open copy of the data, and make the reader fast enough that you never need a second one. No garbage collector to stall it, one storage layer, and aggressive skipping. That is how a lake starts answering fast lookups in milliseconds. Deltaforge comes at this from its own angle. An engine written purely in Rust, built around one idea: optimize the reads and the writes, and on standard open delta tables, it reads and writes 4 to 5 times faster than Spark. One open copy, and an engine finally fast enough to use it.